Hey, Blue Squadron here, welcome back, and we're going to start this video with the code that drives the Upsilon class shuttle. The first thing you may notice about this code is that I have engine pins defined, but instead of using D0, 1, and 4, and 3, I'm actually using PB0, PB1, PB3, PB4. These are internal pin names that are unique to the AT-Tiny series of microcontroller. The engines are pretty easy to program. I just take the PB3 pin where the LEDs are going to be connected, and then set that pin mode to output, and then turn them on inside of the setup function, which of course runs when the AT-Tiny 85 first gets powered on. The cockpit is a little more complex. You'll notice that I've got an array of cockpit values. That's because I want each of the LED pins to be rising in value while the previous pin is fading. So in other words, I'll have to set each of the independent LEDs together at the same time using the set cockpit function, which essentially flashes all of the values to each of the cockpit pins. You'll notice to do that, I'm using this analog write function, and in the Arduino implementation for the AT-Tiny 85, it only works with PB0, 1, and 4, which is something that I found out the hard way. Inside of my main loop, you'll notice that I have essentially a variable that keeps track of which pin is beginning to become brighter. And each time I run through the loop, I'm increasing the brightness of that pin while decreasing the previous pin by the same value. And now you'll notice that I'm subtracting a variable called rising direction. That's because it can either be positive or negative. In other words, if the rising pin is 2 and the rising direction is a positive 1, that means pin 2 is rising while pin 1, in other words 2 minus 1, is falling in value. I have a loop that goes through each of those cockpit value arrays and sets them to safe values, in other words, not lower than 0, not greater than 255. And then finally, if the current pin has reached its maximum brightness, then essentially what I'm doing is I'm changing the direction of which one is the rising pin and the rising direction. In other words, the rising direction switches, and you notice there is a small delay which allows essentially that bounce back from the LED on either the left or the right of the cockpit to stay bright for just a little bit longer. Finally, after setting all of the values inside of the array, I simply call the setCockpit method. I can flash the AT-Tiny 85 controller using that SparkFun AVR programmer pretty much in the same way that you would program one of those Adafruit trinkets. You plug the chip into the programmer and then use the same settings and then just hit program and it just works. Once the program's been flashed onto the chip, I can start working on this breadboard where I'm using it to prototype the circuit just to make sure that everything works. If you've never worked with a breadboard before, you have to know that each of those columns on the far left and far right are what are called the rails. They have a blue and red stripe indicating a positive and negative rail, and those are typically used for carrying power. Each row of the breadboard, it has a whole bunch of pins, and each of those pins are actually connected to each other by the row. So remember, the columns of the rails are connected, and each of the breadboard rows are connected. In other words, if I plug two things into the same row on the breadboard, they'll be touching each other and essentially be electrically connected to each other. I'm using some jumper wire to create the connections between the positive and negative rails directly to the positive and negative pins on board the AT-Tiny 85 chip. You may also notice that partition down the center of the breadboard. That means the rows on the left are not electrically connected to the rows on the right. In fact, it's designed to accommodate integrated circuits, much like the AT-Tiny 85. So I've connected the left blue negative rail to row 11, which is also where the negative pin is touching on the AT-Tiny 85, and I've done something similar for the positive pin on the AT-Tiny 85 and the positive rail. Next, I connect each of the LEDs and the resistors to the pins on the integrated circuit, in other words the AT-Tiny 85, and then to the common ground, which is going to be represented by those blue rails. The pack of resistors that I had didn't have a single resistor that was 150 ohms. That's actually pretty rare in terms of resistors to find one of specifically that value, so you're usually going to have to mix and match for the prototype circuit and get something that's equivalent to 150 ohms. In the final model, I managed to order some 150 ohm resistors off of Amazon.com, and they were actually pretty expensive because they're kind of non-standard. To test the circuit, I plugged in a PowerBoost 500C, and then connected the 5V and ground connections to the positive and negative rails on the breadboard. Once I plug in the chip, I should be able to see whether or not the program and the circuit works. I used a multimeter to make sure that the 5V connection had the correct polarity. Since there's no diode protecting the chip from what's called reverse current, I needed to make absolutely sure that it was 5.1 volts in the correct direction. Finally, I pulled the chip off of the programmer and then plugged it in. Now, you'll notice this first time, the lights don't actually do what I intend them to do. This is why you prototype, because if you build the circuit and then try to solder it all together, you're going to be real sad if it doesn't work the first time. On my second attempt, I corrected the wiring and the program, and this time when I plugged it in, it does what I wanted it to do. You'll notice that 3 of those LEDs are pulsing back and forth, giving me that Cylon visor glow pattern. Now that I've verified the circuit, in the next video what we're going to do is we're going to solder it all together. Thanks for watching.